Okay, we're going to do this next, finish this up hopefully in one video. Laura places a bottle of water inside a cooler. As the water cools, its temperature, C of T in degrees. Okay, so this is our temp in Celsius, is given by the following function where T is the number of minutes. Okay, so this is our minutes since the bottle was placed in the cooler. So we got the function. Laura wants to drink the water when it reaches a temperature of 17 degrees Celsius. So the only reason we're reading this is to know what this is and what T is. Okay, so now it gives us this, so it tells us that we're going to put the 17 for C of T. So we now have this. Okay, so here's what we have to do. When we're trying to solve for a missing variable and it's in the exponent, what we've got to do is first get this part by itself. Okay, we've got to isolate that. So the way we're going to do that is we're going to get rid of the 7 by subtracting it. At that point, that goes away, and we have 10 equals 15e to the negative 0.038t. Okay, we're still trying to isolate e to this power. We've got to get rid of this 15. Well, this is multiplication, so you solve by dividing. You're going to divide both sides by 15. So what happens, we now have this isolated, our e to the negative 0.038t, all by itself. Over here, you can leave this as 10/15ths, or you can reduce it, and I'm going to reduce it to 2/3. It doesn't really matter, because we're going to end up using our calculator anyway. So, okay, now the problem with this here is we've got to free up our exponent. Because our t is in our exponent, we've got to get that exponent to drop down, or we need to free it up. Okay, using our basic properties of logarithms, what we want to do is take the log of both sides. And because this has a base of e, we want to take the natural log of both sides, because what's going to happen is this has a base e, this has a base e, and that cancels each other out. Well, what you do to one side, you have to do to the other, so we need to take the natural log of this side as well. Okay, so at this point, we have the natural log of 2/3 equals, and what that did by doing this, they canceled out, it frees that exponent up to give this. Now it's just a regular problem like every other thing. We need to free up our t. We need to isolate or get t by itself. This is multiplication, so you solve by dividing. You divide both sides by the negative 0.038. So, if I had asked for an exact answer, this whole thing would be our answer. But because it says round your answer to the nearest tenth, and it's a word problem, okay, this would not make sense as a word problem answer. So what we're going to do is we're just going to do this. We're going to take the natural log. Oops, let's see if I can get this. Natural log of 2/3 divided by negative 0.038. And it says round to the nearest tenth, so it's going to be 10.7. So I'm going to do approximately 10.7, and T stands for minutes, so it's 10.7 minutes. And now we're done. Okay. A radioactive substance decays according to the following function where y sub 0 is the initial amount present. Okay, so that's the initial amount. And y let's put here, I should write that out, initial amount, and y is the amount present at time t. So this is the amount at time t, and this is our time. So now it says, find the half-life of this substance. Okay, this is just a, not a generic, but this is just a formula that when we talk about half-life and it doesn't give you any numbers, you can use any number you want for y sub 0. Any number you want. But I'll give you a hint, you always want to pick an even number, okay? I'm just going to pick a round number like 100. You could put 200. You could pick 50, anything you want for the initial amount. So I'm going to use 100. So if we're talking about half-life, they'll use this a lot in science. It's the time it takes for something to go down half of its mass. So if the initial is 100, then y is going to be, in its half-life, would be 50. Okay? So if this had been 200, this would be 100. If this was, let's say, 80, this would be 40. Okay, so now let's fill in what we know. So we have 50. Our initial was 100. E to the negative 0.062 t. Okay, because we're trying to find the time of its half-life, okay, we need to get this by itself, just like we did up here, okay. We're going to divide by 100 to get that by itself. The reason these numbers do not matter is because when you reduce this, it becomes 1/2. And we have that. So if this had been, let's say, 80, after the half-life would be 40. And you would have 40 divided by 80, which reduces to 1/2. That's why it doesn't really matter what number you pick here. Then half of that is going to be here, because it will always reduce down to 1/2. Okay, seeing this as a base e, we need to free up our exponent. We're going to take the natural log of both sides. What happens is that cancels each other out. Over here we have the natural log of 1/2. Here it frees up our exponent. Now what we're going to do is we got to solve for t, so we're just going to divide by negative 0.062. So I'm going to do the natural, let me clear this out, see if I can get it so there's no glare. 1 divided by 2, natural log of 1/2, divided by negative 0.0, yeah, it doesn't matter if you have a 0.062, and that's going to give us 11.2. And our time was in days. Okay, so it's 11.2 days. Is approximate. T is approximate that. Okay? It's not too hard, you just got to remember this step. Alright. 2 more problems. Alright, finding the rate or time in a word problem on continuous exponential growth or decay. Alright, if 20,000 is going to be invested in an account for 10 years, that will be compounded continuously. That is this formula right here. We've already used that a couple times already. Determine the interest rate that would allow the money to double, round to the nearest 1/10%. Okay, on this right here, so we're investing $20,000. So that goes for P because that's what we're initially investing. Okay. If it's going to double, so you just do 2 times this, which is going to get, we want to know when it's going to, or the interest rate that allow it to double, when it reaches 40,000. Okay. Let's see, 10 years, that is our time. So our T equals 10. So this was our P. Okay, the P equals 20,000, not 20, but 20,000. And then because it says double, our amount would be double that, which is 40,000. If it was to triple it, then you'd say 3 times that and give you 60. All right. E to the, we're trying to find our rate, and our time is 10 years. Okay, just like before, we got to get this by itself. To do that, we're going to divide by 20,000. And we get 2 here. Over here we get E, and I'm going to switch this around. Instead of R times T, I'm just going to put 10R. Now again, to free up our exponent, because this has a base E, we're going to take the natural log. So you got to do it to both sides. So I get the natural log of 2 equals E to the 10R. Oops, no we don't. Sorry. I'm like, wait a minute. This cancels that out, so we have 10R. Now you divide by 10. And it says round to the 10th of a percent. So when you do this, natural log of 2 divided by 10. And it, oops, well, see what I did? That's not what it is. I always forget they put their parentheses, okay? Be careful. I knew something was wrong when it came up to be negative. The natural log of 2, I have to close my parentheses there. Now I'm going to divide that by 10. And I get this right here, which is 0.06931, blah, blah, blah. Okay, doesn't really matter. But what we've done is we've taken this and made it a decimal. We need to go to a percent. So it's going to move over 2 places to the right because we're multiplying by 100. And our rate is approximately 6.9%. Don't forget to do that. Okay. All right. The number of bacteria in a certain population increases according to the continuous exponential growth model. Well, they've never given that to you. Okay, so I will. It looks like this. Looks really similar to this up here. Okay. E to the RT. The key thing in all of these is these here, those are what we start with. That's our initial. Okay, our initial amount. Okay, so the number of bacteria increases according to this with a growth rate of this percent per hour. You got to change that to a decimal so it moves left 2 places. So our rate is going to be 0.027. And it says, how many hours does it take for the size of the sample to double? Again, this is similar to the other one with the half-life. Pick a number to start with, okay? Last time I picked 100, okay? I'm going to pick, let's say 400. It really doesn't matter, okay? If my initial is 400 and we want to know the size of the sample to double, you're just going to say 2 times that. So from there to there, that's where you get the double. You just double it. And now you fill in what you know. And again, it doesn't even matter about these two numbers. Just pick some number and then double it. And then fill it into this equation. And our R is 0.027 t, because we're trying to find how many how many hours, right? How many hours. Okay, so I'm going to divide by 400 to get that e by itself. That cancels. We have 2. The reason it's not going to matter over here is because whenever you take a number and double it, and you'll get this ratio here, which will always end up to be 2 because they were doubling it. And we have this here on the right hand side, e to the 0.027t. Again, I have to free up this exponent. I do that by taking the natural log of both sides. And what happens is that cancels that out to free up our exponent. So we have the natural log of 2 equals 0.027t. Now just divide by 0.027. And t is going to be approximately, and be careful when plugging this in, don't make the mistake like I did up here, okay? You're going to do the natural log of 2, you need to close those parentheses, divided by 0.027. And it's going to give you about 25.7 hours. Be careful, because you have to close those parentheses. 25.7 hours. And that's it.